we're going to begin this lecture by looking at some of the historical facts surrounding the early days of organic chemistry, how it developed as a unique field, why you're studying organic chemistry, why do we have a whole course devoted to one element, and then we're going to begin looking at some of the elementary features of structure and bonding. Okay, so organic chemistry is the study of carbon-based compounds. You may be wondering, why do we have two courses devoted to one element? And the reason is because carbon forms strong bonds with itself and virtually every other element except the known gases, noble gases. Carbon engages in 3 different bond types, and the number of combinations that can give rise to stable compounds is probably infinite. It's also no secret that living systems depend on carbon. Okay. Just to give you an idea of how important organic compounds are, I'd just like to point out to this diagram here. This is the old way we used to search literature through I guess we call it a search engine, or it's just called chemical abstracts. Okay, chemical abstracts would have something called a formula index that they would publish every 5 years. And it would start with actinium and go all the way to zirconium. And in our first issue here, we would see the beginning of it with actinium to organic compounds with 3 carbons. Then it would go through several volumes, like here we would see something like C4 to C6, and then C6, C7, all the way to the last one, which is then C32 up to zirconium. What we see here is that the vast majority of this little book is devoted to organic compounds. Okay, so most of the compounds known are organic compounds. If we look at completely inorganic compounds, we find that only a small portion of the known substances is really devoted to them. Okay, so this is inorganic also. Alright, so this establishes the sheer dominance of organic compounds amongst all the known compounds. Okay, why the word organic? Organic implies living things, wholesomeness, and we'll find that many parts of organic chemistry are anything but wholesome. Okay, so you have to go back to the 1850s, when we had 2 types of chemists that were studying matter. Inorganic chemists, they studied rocks, minerals, or compounds derived from them. These compounds were often crystalline. They were never volatile, and they're often colored. Organic chemists studied compounds that were derived from living or once living, like oil or coal systems. These compounds were often liquids, or if they were solids, they had low melting points. They often had odors, and they were usually either colorless or yellow what few times that they were colored. Okay, so these 2 branches used very different techniques to deal with their compounds, and these chemists really, at the time, thought they were working in different fields. Until one day, this important experiment here, the Wohler urea synthesis, converted an inorganic compound, ammonium cyanate, into an organic compound known as urea, which is the major non-water component of urine. Okay, so this experiment sort of taught people that organic and inorganic chemists weren't really working in different fields, and today there's a lot of overlap between the fields of inorganic and organic chemistry. We don't change the rules of structure and bonding just because we have an inorganic versus an organic compound. Okay, let's look at some of the modern contributions to organic chemistry, or the modern contributions that an organic chemist has made to our life. Okay, nutrition and food supply. Organic chemists have isolated, characterized, and prepared virtually every substance in our diet. We know the structure of all the vitamins, most of the flavor ingredients, all the carbohydrates, fats, and proteins that are in our bodies and in the foods we eat. Organic chemists have also made a big contribution through crop protection. Due to fertilizers and pesticides, only about 2% of Americans are employed directly in agriculture now. So before these inventions, it was more than 50% of the people were engaged in the production of food. Medicine, greater than 95% of all prescribed and over-the-counter medicines are unnatural organic compounds that were designed by biologists and chemists working together and synthesized by chemists and chemical engineers working together. Important advances in antibiotics, anti-cancer, antifungal, and anti-inflammatory medicines have made great improvements in our lives. We don't worry about dying at age 30 from a bacterial infection in most cases, and we continue to make advances in these areas. A high percentage of the employees at any pharmaceutical company are organic chemists. Luxuries include fuel and energy, gasoline, natural gas, coal, ethanol, biomass. All of these are organic compounds, and you have to manipulate them to turn them into useful substances. Polymers and plastics like nylon, polyester, rayon, orlon, spandex, PVC. These were all invented by organic chemists. Okay, biological systems can be described as a series of interactions and transformations involving mostly organic compounds. Okay. There's some negatives associated with organic chemistry advances. Organism resistance. This is particularly true with pesticides and antibiotics, although we're learning now certain things that probably should have been common sense, like after a bacterial infection appears to be over, keep treating it to kill all the more resistant bacteria. But there's still a problem with antibiotics, and that a high percentage of them are based on maybe 5 or so lead compounds. So they're So there's still a lot of room for improvement in the design of new antibiotics. Many of you know that most of the early studies about toxicity and effectiveness of drugs and various other artificial ingredients were approved based on short-term effects that could However, some of these things had long-term effects that could have never been envisioned or never been imagined in the short-term evaluations that they were used to approve of these substances. And then there are abuses of chemicals like illegal drugs and steroids. Organic chemists we're important, but we often don't stand out as the forefront. When I look for like media heroes who are organic chemists, you really have to stretch quite far. Okay, so one I guess Clark Griswold in the movie Vacation was described as a genius with food additives. So I guess he was an organic chemist. Walter White, many of you know as Heisenberg on the Breaking Bad series. Okay. All right, so I have a problem with the pen here. It's extremely sensitive. Let me go back. Okay, so Walter White, of course, he's an organic chemical educator, a practicing organic chemist, drug kingpin, and a fellow New Mexican. Okay, so he's not exactly what you would call a positive voice for organic chemistry, but there are occasionally things that appear in the media that the organic chemist can relate to. If you watch modern day shows like CSI, there is a lot of organic chemistry phenomenon mentioned in those shows as well. Okay, let's look at now some of the raw material. We're going to first start off by looking at chemical bonding. There are 2 to 3 bonding types that are important in organic chemistry, depending on how you classify the last one. Bonding is driven by the desire to achieve a noble gas configuration of all the atoms and to maximize the number of bonds. Bonds, throughout this course, you have to remember, are a good thing. They're stabilizing. It's the formation of a bond is always an exothermic or favorable reaction. Okay, so we have 3 bonding types. Ionic, this is between 2 atoms with extreme electronegativity differences. They're on opposite sides of the periodic table. We have covalent bonds. These are between 2 atoms with similar electronegativity. And we have polar covalent bonds, which is kind of a hybrid between ionic and covalent. So this is that 3rd bonding type, depending on whether you count it as a separate bonding type or as a hybrid bonding type. We say there are 2 to 3 bonding types in organic chemistry. Okay, so let's just look at Lewis dot structures. These show the distribution of valence or outer shell electrons. So ionic bonds, a good example of these would be elements where at the opposite sides of the periodic table, where there are extreme differences in electronegativity. Compounds like sodium chloride, lithium fluoride, potassium hydroxide, I mean specifically the potassium oxygen bond here, not the OH bond, magnesium bromide. All of these are good examples of ionic compounds. Okay, so if we want to look how an ionic compound is constructed, we're basically just giving the electron here from the element that's not so electronegative and giving it to the element that is electronegative. Okay, so everybody's happy. The bond between sodium and chlorine is just the attraction of a positive charge for a negative charge. Okay, ionic compounds typically have extremely high boiling points. They're almost always solids due to a complex network of ionic attractions. In other words, even though I showed that sodium near that chlorine, there's another chlorine out here that's attracted to the sodium, and then there's other sodiums attracted to the chlorines. So all of this is occurring. Okay, they also typically have very high water solubility. As we discuss organic chemistry, we'll discuss the boiling point as the major measure of the attractive forces between molecules, and water solubility is a property of that can be described as like dissolves like. Water is a very polar molecule, and things that are very polar tend to dissolve in water. Okay, at the other extreme are covalent bonds, and these occur when we have elements that are of similar or identical electronegativity. Good examples of almost purely covalent bonds are hydrogen, fluorine, chlorine, and the CH bonds of methane. Okay, so let's look at how we make a covalent bond. Okay, so fluorine atom has 7 electrons buzzing around it. Okay, so if we just pair up these 2 electrons, we get now a bond between fluorine and fluorine. This bond represents equal sharing of this electron pair right here. Okay. Lewis structures just have too many dots all over the place. They're a little bit confusing. An organic chemist is more likely to go with a Kekulé structure, and this is where we're showing the bonding electrons as a line. Each line implies an electron pair. Okay. When we're doing Lewis structures, one of the things we do with each atom is that we maximize the number of unpaired electrons so that we can get as many bonds out of the compound as possible. So carbon has 4 valence electrons. The best way you can distribute these 4 electrons is for a Lewis structure is to just have them as single unpaired electrons. Okay, so the hydrogen here, 4 of these will get together and we'll have 4 covalent CH bonds. There's very little electronegativity difference between C and H, so these bonds are predominantly covalent. Okay. Alright, so we do this so as to get the maximum number of bonds. A little later in this class, we're going to take another look at this. We're going to look at the actual orbitals that are involved in doing this. Okay, but for now, we're just going to look at the basic distribution of electrons. Okay, polar covalent bonds occur when we have elements that are quite different in electronegativity, but not different enough to call them ionic. The best example I can give of a polar covalent bond is HF. Okay, other compounds like water, ammonia, and CF4 also have polar covalent bonds. Okay. So here, just like with a purely covalent bond, we are sharing the electrons between H and F. Okay? But the sharing's not equal because hydrogen's not all that electronegative and fluorine is extremely electronegative. So these electrons in the bond spend more time around fluorine than they do around hydrogen. So they're not evenly shared. Okay, this presents a bond dipole when we have this situation. This means this is the positive end of the dipole. And this end is the negative end. Of the dipole. Okay? In the vast majority of organic compounds, since we're dealing with compounds of carbon, and carbon's in the exact middle of the periodic table, we're dealing with covalent and polar covalents as the predominant bond types. Okay. Bond energy is measured by a quantity known as the bond dissociation energy, which is delta H for the what we call the homolytic breaking of a bond. Okay, so here we have two electrons, and one of them's going to go to that side, one of them's going to go to that side. It's just cutting in half to the free atoms. This reaction is always endothermic, i.e. delta H is a positive number, and the higher the number, the stronger the bond. Okay. Throughout this class, what we periodically do is go through problems. This is a problem. What you should do right now is pause the video and answer the question. I'm going to just go through it because you can pause it if you want to work through the problem. Okay, so what we're looking at to do here is identify whether each bond is ionic, covalent, or polar covalent, and recognize that, of course, polar covalent versus covalent, that's a little bit of a continuum, so kind of a gray area if we have two different atoms involved. Okay, this is a covalent bond. It's very slightly polar. Hydrogen's electronegativity, I think, is 2.1, and carbon's is 2.4. The potassium-oxygen bond is an ionic bond. Okay, there's quite an electronegativity difference between potassium and oxygen. And the CO bond is definitely a polar covalent bond. Okay, let's look at some additional Lewis structures and look at a situation that we frequently encounter in organic chemistry, and this is called multiple bonding. So let's look at H2CO. This is the molecule formaldehyde. Okay, common preservative. Okay, so if we want to imagine how this molecule gets put together, we can add the hydrogens here to two of the bonding sites at carbon, and we can form a bond right here between C and O. Okay, so what that gives us is this one. However, we're still left with only 7 electrons buzzing around carbon and only 7 at oxygen. So we can actually make an additional bonding electron pair by taking these unpaired electrons, and this gives us the double bond right here. And so we say that we have a carbon-oxygen double bond in formaldehyde. Okay, similar compound is this one, ethylene, and it's a lot like formaldehyde except that it has a carbon-carbon double bond instead of a carbon-oxygen double bond. Okay, so we're doing the same pairing up of 2 electron pairs here, just like we did with formaldehyde, and this gives us the carbon-carbon double bond. And recognize that with the double bond, each carbon has some shares in 8 electrons, as does the carbon and the oxygen in the structure up here. Okay, we can go one further. Hydrogen cyanide is simplest molecule where we can have a carbon-carbon triple bond. Okay, so recognize that when we do this pairing up here, that we get now 2 sets of unpaired electrons, and we can pair each of them up, and we now have a triple bond. Okay, carbon has shares in 8 electrons. Nitrogen has a lone pair and 3 bonds, so it also has shares in 8 electrons. Okay, So these are the three types of bonds that we can have in organic chemistry. We can have single bonds, double bonds, and triple bonds. It doesn't get any higher than that in organic chemistry. Okay, let's just look at some effects of bonding and bond strength on bond length, and I want to concentrate here just on the CC bonds. We'll deal with the CH bonds a little bit later. Okay, what we see here is that as we go from a single bond to a double bond to a triple bond, the bond is getting shorter. This is an indication that there's a stronger attractive force between the two carbon atoms. Okay, if we look at the bond dissociation energy in kilojoules per mole, we're also seeing that it's getting stronger. The double bond is stronger than a single bond, not twice as strong though. 2 times 375 is 750, and we'll get into the significance of that when we talk about carbon-carbon double bonds. And the triple bond is even stronger still. Okay, well, we're going to revisit this when we talk about compounds that actually have double bonds and triple bonds in them later in the class. Okay, but this is an effect that we should be aware of, that when a bond is stronger, it has a stronger bond dissociation energy, and often, but not always, when we're comparing similar elements, the stronger bond is the shorter bond. Okay, so here's one problem we'll leave you off. You should, again, pause the video here so that I don't quite get the answers. Try to draw calculating structures, including the lone pairs for each species, and I'll go immediately to the answers, but you should do the problem first before you look at the answers. Okay, so let's look at HNO. Nitrogen is the central atom. Okay, here's a structure we can write that has 8 electrons at nitrogen and oxygen. Okay, cyanamide is the next compound down here, and we can draw again a nice structure that has 8 electrons at every carbon and nitrogen atom by drawing a carbon-nitrogen single bond, or a carbon-nitrogen triple bond here, and the carbon-nitrogen single bond over here. Okay, let's see, this next compound, 2 nitrogens in the middle, carbons on the outside. We can draw a nice Kekulé structure like this, where all carbons and nitrogens also have 8 electrons. And finally, we'll look at this last structure, which is called ketene. And here we can draw a structure of this type where the central carbon is part of 2 different double bonds, but as long as we don't exceed 4 bonds at carbon, or exceed 8 electrons at nitrogen and oxygen, that's okay. Alright, so I'm going to end the video here. This will pick up with the video that's called Part 2.